These are the answers to homework 5E. Here are the definitions I'd like you to know. Now let's go to the questions. Number 1, a 3.50 gram sample of a compound containing only carbon, hydrogen, and nitrogen was burned, producing 3.35 grams of carbon dioxide and 4.11 grams of water. The effusion rate of this compound was measured and found to be 24.6 milliliters per minute. Under the same conditions, the effusion rate of argon gas was found to be 26.4 milliliters per minute. Part A, determine the empirical formula of the compound. The information given in the problem to allow you to calculate the empirical formula were the combustion products of the compound. When the compound was combusted, which means reacts with oxygen, you would form an oxide of carbon, CO2, an oxide of hydrogen, H2O, and some oxide of nitrogen, which wasn't mentioned in the problem. To figure out the empirical formula, we're going to calculate from the mass of the carbon dioxide how much carbon is in the carbon dioxide, because that's going to equal the amount of carbon in the original compound, because that's the only place the carbon came from. Knowing that the molar mass of CO2 is 44.0 grams, and out of that, 12.01 grams of it is carbon, if I multiply the mass of CO2 by that fraction, 12/44, that's going to tell me how many grams of carbon are in the CO2, and therefore that's how much carbon is in the original unknown compound. From the mass of water produced, we can calculate how much hydrogen is in the original compound, because all the hydrogen in the compound wound up in the water. The molar mass of water is 18.02 grams, and out of that 18.02 grams, 2.02 grams of it are hydrogen. So if we multiply the mass of water by the fraction 2/18, that's going to tell us the mass of hydrogen in the water, and therefore that's going to be the mass of hydrogen in the original unknown compound that was burned. We weren't given a product with nitrogen, but by subtraction, we can figure out how many grams of nitrogen must have been in the compound. If they burned 3.50 grams of the unknown, and it contained 0.914 grams of carbon and 0.461 grams of hydrogen, if we subtract out the carbon and hydrogen, all that's left over is the nitrogen. So therefore, the mass of nitrogen in the compound must have been 2.13 grams. Once we know the mass of the three elements that make up the compound, now we can do the empirical formula determination. We'll convert the grams of each of these elements into moles. So the number of moles of carbon in this sample were 0.0761. The moles of hydrogen in this sample were 0.456. And the moles of nitrogen in this sample were 0.151, pointing out one more time here, when we're doing an empirical formula determination, you're trying to find out the number of carbon atoms, hydrogen atoms, and nitrogen atoms. That's why I'm using the molar mass of monoatomic hydrogen and monoatomic nitrogen. I'm not trying to find how many diatomic hydrogen molecules are in the formula or how many diatomic nitrogen molecules are in the formula. The final step is to divide each of the moles by the smallest number, which is the moles of carbon. And when all of those are divided by 0.0761, we get 1 mole of carbon to almost exactly 6 moles of hydrogen to almost exactly 2 moles of nitrogen, which means the empirical formula is CH6N2. B, determine the molar mass of the compound. The data given in the problem that's going to allow us to determine the molar mass are the effusion rates. Because if we have two gases under the same conditions, which means same temperature, that means their kinetic energies are going to be equal to each other. And if their kinetic energies are equal, we can say 1/2 mv squared for the argon gas must equal 1/2 mv squared for the unknown gas. The m's are the molar masses, the v's are velocities or effusion rates, which are given in the problem. To solve this for the molar mass of the unknown gas X, I'll cancel out the 1/2s on each side of the equation and then divide both sides by the effusion rate squared of the unknown gas. Now all we have to do is plug the numbers in. Argon is a noble gas, it's monoatomic, so its molar mass is 39.95 grams per mole. The argon's effusion rate was 26.4 milliliters per minute, and you have to remember to square that. And the effusion rate of the unknown gas was 24.6 milliliters per minute, and you have to remember to square that. The milliliters squared per minute squareds cancel out, leaving the units of grams per mole into 3 significant figures. The molar mass of the gas or the compound must be 46.0 grams per mole. Part C, determine the molecular formula of the compound. So now that we know its empirical formula and we know its true molar mass, the next step is to calculate the molar mass of the empirical formula. So if the empirical formula is CH6N2, I'm going to add up the mass of 1 mole of carbon, 6 moles of hydrogen, 2 moles of nitrogen, and that comes out to be about 46.08 grams. I see how many times this number divides into the true molar mass of the compound, which happens to be 46, and 46 goes into 46 one time. So that means in this case, the real molecular formula is just the empirical formula times 1, turns out to be CH6N2. Question number 2. Table 5.3 of the textbook, which gives van der Waals constants, does not give the van der Waals constants A and B for gaseous bromine. Predict their numerical values and explain your reasoning. So what is in the table in the textbook is the A and B values for diatomic chlorine. And bromine and chlorine are related to each other. Let's first talk about the A values. A corrects for attractive forces. The more attractive forces gas molecules have, the bigger the A constant has to be to correct for that. So how do attractive forces in chlorine and bromine compare to each other? Well, bromine and chlorine are both nonpolar molecules, and they attract only with London dispersion forces. But bromine molecules have more electrons, so that means they're going to be more polarizing, so they should have stronger intermolecular attractions. That means the A value for bromine has to be bigger than the A value for chlorine. So if you picked a number greater than 6.49, that would be acceptable. What's the reason for that? Well, bromine has stronger LDFs than chlorine does, and the more electrons a molecule has, the more polarizing it is to other molecules. The greater the instantaneous dipole moments, the greater the attractions. So bromine gas would need to have a bigger A value in order to correct for its stronger intermolecular attractions. The B value corrects for molecular size. And because bromine atoms are bigger than chlorine atoms, that means a bromine molecule would have to be bigger than a chlorine molecule. So I would expect the B value for bromine to be bigger than the B value for chlorine. And that would be just because the bromine molecule is larger than the chlorine molecule. Number 3, calculate the pressure of 0.5000 moles of nitrogen gas in a 10.000 liter container at 25.0 degrees using A, the ideal gas law equation. This is PV equals nRT. We're going to solve for the pressure. I'm just going to plug the values into the equation along with the universal gas constant. So the moles, 0.5000, universal gas constant, 0.08206, the temperature switched to Kelvin, 298.2, and the volume of 10.00 liters. Moles, liters, and Kelvin cancel out, leaving the units of atmospheres, and to 4 significant figures, the ideal gas law equation would predict that this particular gas would exert a pressure of 1.224 atmospheres. If we want to account for the fact that molecules actually attract and take up space, we would have to solve for the pressure using the van der Waals equation, and that would require you looking up the van der Waals constants for nitrogen gas. If you solve the van der Waals equation for pressure, it's going to equal nRT over V minus NB minus A times quantity N over V squared. The first term here would be the moles multiplied by the universal gas constant multiplied by the temperature divided by the volume minus the number of moles multiplied by the B constant, 0.0391 liters per mole. The second term would be the A constant, 1.39 liters squared atmospheres per mole squared, multiplied by N over V quantity squared. In the first term, all the units cancel out except for atmospheres, and we get to 4 significant figures, 1.226 atmospheres. In the second term, all the units cancel out except for atmospheres, and we get to 3 significant figures, 0.00348 atmospheres. Subtracting these 2 numbers, we go by columns past the decimal point. The first term only is accurate 3 places past the decimal point, so the answer will have to be rounded 3 places past the decimal point, and that comes out 1.222 atmospheres. So as would be expected, the pressure of the real gas would be slightly lower because real gas molecules attract, so the molecules don't hit the inside walls of the container quite as hard. But in this case, the difference between the ideal gas law equation and the van der Waals equation is only 0.2%. And so for that very small difference, that's the reason why the van der Waals equation is hardly ever used.